Welcome to our ACT lesson on plane geometry. I am Ben Flores here at Testive, and I'm going to be talking you through the lesson today. All right, so what is plane geometry? Plane geometry, well, first, plane geometry is a section on the ACT, and it makes up 20 to 25% of all ACT math test questions. So it's really important for you to get the skills that can make these questions easier for you to tackle on the ACT. So plane geometry is the study of the shapes that you're seeing in front of you, and it involves geometric notation. It involves calculating angles in a plane, calculating the angles of a triangle. It involves a lot of formulas that are based on triangles, areas and perimeters, calculating those in the shapes that you see in front of you, like a cube, a rectangular prism, cylinder, triangular prism. Calculating the area and circumference of circles. It involves some solid geometry, and it also involves this thing called concept of proofs that sounds maybe tricky, but at the end I'll show you that it's not a big deal. Plane geometry is not the creation or interpretation of formal geometric proofs. It's not coordinate geometry. You can see an algebra lesson for that. And finally, it's not trigonometry, which is what you're seeing below you with sine, cosine, tangent. That's all a whole different branch of math that you'll find on the ACT. So today I want you to record a cheat sheet for yourself. So basically, I just want you to get a piece of paper, and I want you to log anything you see that you don't know cold. So any formulas that you see today, or manipulations you see where you don't know them off the top of your head. And that should just fit on a single piece of paper, no problem. Okay, so the question is for plane geometry is how can you get better at answering these questions? Today we're going to make sure that you can identify the question type, complete a picture that's presented to you. You'll need to know the formulas, right? So you'll need to be able to have a few formulas in your memory that you can manipulate to get the right answer. One thing that you're going to be able to do to help yourself, and we're not going to cover this much today, is like jotting a lot of notes for yourself, writing down as much as possible when you're facing a question you don't know. And treat the questions as a puzzle. Basically, in plane geometry questions, there's often one thing missing. You have all the pieces that you need to figure out what that missing piece is. It's just figuring out how to put them together in the right way. So some notation that we're going to be seeing today. We're going to be seeing similar length, similar angle, and parallel lines. So as you can see just right over here as you can see right here, these notches show that two lines are the same length. These arcs show that two angles have equal measure. And these little like bracket notches show that, or arrow-shaped notches show that two lines are parallel. All of this is going to be important for us today. Okay, what's next here? So angles, vertical and supplementary angles. We're going to take a look at two different kinds of angles here that you're going to see a lot of on plane geometry questions. You're going to see vertical angles. These are angles that, for sort of lack of a better way of putting it, the way to think about it is they are across from each other. So you can see that they're across from each other and they are similar. So angle A is of equal measure to angle C here. Remember, if we go back, you can see this arc that shows that the angles are equal measure. If we go forward, we can see that A and C both have that arc and that they are equal measure. So supplementary angles are a little bit different. Supplementary angles are angles that are along the same line, right? So this line here, you can see that A and B, the angles A and B are both along this same line. And we know that a straight line has an angle measure of 180. So A plus B is going to equal 180. So if we know one of these angles, we can easily find the other angle by subtracting from 180. All right, so We have an example of that right here. We have angle A is 135 degrees, and we don't know what angle B is. Well, that's pretty straightforward. I'm going to give you a moment to think about it. So we know that this line right here has a measure of 180 degrees because it's a straight line. So A plus B is going to equal 180. And so therefore 180 minus 135 is going to equal B. And we know that B is going to be 45 degrees. All right, pretty simple. Okay, so this is a little trickier, but it's the same thing. Like I said, that missing puzzle piece. We actually know one of these pieces, so we can find the next one. So we can see that A and C are vertical angles. So we know that A and C are both 135 degrees. And we know that B, well, we already figured that out. We know that B is 45 degrees. If we know that C is 135 degrees, then, well, that means we know what D is as well. D is also going to be 45 degrees. And we don't need actually B or C to know that. We just need D and A. A is 135 degrees plus 45 degrees, gives us this straight line of 180 degrees here. This question here is actually asking us for B plus C plus D. So I'm just going to do quick mental math here. I know that B plus C is 180 degrees, 45 plus 135. And then I know that if I add another 45 degrees, that's going to be 180 plus 20 is 200 plus 25 is 225. Okay, triangles. Triangles, there's just the very first thing you need to know about triangles is that they have angles that sum to 180 degrees. Without remembering that, you probably won't get anywhere, but if you know that, that can even just take you some of the way, just knowing that simple fact. So A plus B plus C, the three angles of a triangle, always add up to 180 degrees, no matter how big or small each of them are on their own. So here's a couple kinds of triangle here. We have an equilateral triangle and an isosceles triangle. You can probably figure out, I mean, you probably already know what the difference is, but even if you didn't, you could figure it out just from this picture. An equilateral triangle, we can see these marks here. They show that all three angles here are identical, and all three of these sides are the same length. Equilateral, so same length sides. So we have all three sides of the same length, all three angles are 60 degrees. And over here on the right, we have an isosceles triangle, which is an equilateral triangle that has been changed a little bit by kind of squishing it in or stretching it out. One of the sides is no longer the same length. So two of the sides we can see are the same length. Two of the angles are the same length, but the final side is a different length. And the final angle up here as well is also a different length. Okay. So here's an example. So if we look at this, we know that this is an isosceles triangle. We know it's not an equilateral triangle because it doesn't show us that this final side is the same length. And we see that A and B, though, are angles that are the same size. And we see that side AC right here is the same length as side BC. Right? So AC equals BC, angle A equals angle B, so we know that angle B is also 70 degrees. If we're just kind of filling it out, we're just completing the picture here. There's no question, but we're just filling in information. So we know both of these are 70. All right, so if we know both those are 70, we can also figure out this final angle here. We can also figure out angle C, because we know that everything adds up to 180. So 70 plus 70, excuse my mouse drawing here, it's really messy, equals 140. And then we know 140 plus C is going to equal 180. So we know that C is equal to 40 degrees. Okay, right triangles. So right triangles have a few special things that you can use to solve questions. So one thing that we know about a right triangle is we know why it's a right triangle. It's because it has a right angle. A right angle is shown by this rectangular angle marking here, which means that this angle is 90 degrees. So any triangle that has a single angle that's 90 degrees is a right triangle. And in fact, the triangle can only have one angle that is 90 degrees. If a triangle had two angles that were 90 degrees, that would add to 180, and you would have a straight line, not a triangle. So one special thing, and probably the most special thing about right triangles, is that you can calculate the length of their sides using the Pythagorean theorem. The Pythagorean theorem is kind of for me, it's like the main workhorse of a lot of work in plane geometry. You can figure out a lot knowing the Pythagorean theorem. So Pythagorean theorem is a squared, that's this side here, a. So if you square a squared plus b squared, so take the square of this side here, b squared equals c squared. So the square of the two sides that extend from the right angle, if you add those together, you get the square of the hypotenuse. So what we often think of as sort of like the diagonal. That's not actually right. That's not what we call it, but the hypotenuse. So do not mistake this. Do not mistake this for A plus B equals C. That is not true, and it does not work out. But there is a little shortcut in terms of some sets of numbers that work together really nicely with the Pythagorean theorem. So I don't need to read them all off for you here. I will, but I'm not gonna go through each one. 3, 4, 5. We know 3, 4, 5 works because 3 squared is 9, 4 squared is 16, and 5 squared is 25. 9 plus 16 equals 25. 6, 8, 10, 30, 40, 50, 5, 12, 13. One special thing that you might notice here about these sets of sides, and these sets of sides are sides of triangles that actually work for a right triangle using the Pythagorean theorem. One special thing that you might notice is that each of these is proportional to each one of these is proportional to another one, right? So 3, 4, 5, if we just multiply that by 2, we're going to get 6, 8, 10. Right? So 2 times 3, 4, 5, 2 times 3 is 6, 2 times 4 is 8, 2 times 5 is 10. Right? Similarly, if we multiply, let's see here, say 3, 4, 5 times 10, well, we're going to get 30, 40, 50. Okay, so they're all proportional. Okay. And this last one here, 5, 12, 13, this one is not proportional to the other ones, but it still works out, right? So it's actually, I think, 5 times 5 is 25, 12 times 12 is 144, 144 plus 25 is 169. The square root of 169 is 13. Okay. Which incidentally actually is sort of shows why it's not a plus b equals c, because these three sides don't just have a fixed proportion to one another, right? So if you have one triangle that is a right triangle and you multiply each side by the same amount, you're going to get another right triangle, but that doesn't mean that all right triangles have exactly the same proportion, because of course they don't, because I can show you right here. Here's a right triangle that looks like that. And here's another right triangle that looks drastically different, but nonetheless is a right triangle. And for each of those, I can draw you a smaller right triangle that looks like it has the same angles. But of course, those smaller right triangles are not similar to one another. Okay, so we just kind of did one of these. I gave a little preview here. So a squared plus 12 squared equals 13 squared, right? So I just kind of worked this out for you already. A squared plus 144 equals 169. Therefore, we know that a squared equals 25. If we wanted to actually find a, well, we would need to take the square root both sides of this equation, and we would get that a, of course, equals 5. No problem. Okay, and I also gave a little preview of this here, similar triangles. So if the angles are the same, the sides are proportional, right? So this is kind of messy right here, just this notation here, and I'm sorry about that. But what this means is if you're looking at a triangle like this, okay, if you're looking at a triangle like this, and it has a parallel line within it, a line that's parallel to one of the sides of the triangle. Well, let's think about what we know about what's going on here. Well, we know that AB, for example, is a straight line. So that means we know that angle ADE and angle BDE are going to add up to 180, right? We also know if we were to extend this in this direction, we'd be able to see that, well, if this line is parallel, well then, of course, this angle right here, DAC, is the same as angle BDE. So if we know that, well, then we know that the triangle that we just made inside of triangle ABC, okay, let me actually record a little bit of this here. So we actually know that we have triangle A, B, C, and then inside that we have triangle D, B, E. Well, we know all the angles are the same because we just showed that along this line, angle BDE is the same as angle BAC. And we also know that angle BED is the same as angle BCA. So if all the angles are the same, because they share angle ABC, then we know that the side lengths are also the same, because anytime that you have those triangles that are, or not the same, that the side lengths are proportional, right? So that side length BE compared to side length BC is going to be the same proportion as side length BD compared to side length BA, and finally side length AC is going to be the same proportion to side length DE as the rest of those proportions. Okay, so let's take a look at an example here. So if BE is equal to 4, okay, and BC is equal to 6, and BD is also equal to 6, clearly this is not to scale, then what is BA? Okay, so we can just do quick cross multiplication here. So we know 4 over 6 is going to be the same thing as 6 over x, where x is the length of BA. Okay, so we're going to do 4x equals 36. And therefore, if we divide both these by 4, we're going to get that x equals 9. And side length BA equals 9. One more quick example. If we were to take just with a right triangle, because that might make it a little more straightforward. So it's pretty easy to see that if we take a big right triangle, and then I make a smaller right triangle inside it, and I make a smaller right triangle inside that, well, each one of those triangles is just the same proportions as the triangles that are bigger than it, because it's as if we're just kind of expanding each one of these triangles to get bigger and bigger or smaller and smaller. It's like a zoom on a camera might be one way to think about it. Okay, we could even just imagine it getting bigger and bigger and bigger like that, where everything changes by the same rate at the same time. Okay, so there are a couple special right triangles. There's not much for me to say about these other than that you need to write these down. You need to remember these. Uh, really just commit them to memory because you're going to need to use these relationships on the test. So a triangle that's a right triangle right here with two 45-degree angles. So basically it's an isosceles right triangle, right? It has two identical angles, two identical sides, and one angle that's different, which happens to be a right angle in this case. The sides on that, the sides extending from the right angle are identical, right? So x, x, and then the hypotenuse is x root 2, right? So we can imagine if x were 2, that the hypotenuse would be 2 root 2. Make sense? Okay. Uh, Another one of these special triangles is a right triangle in which the other two angles than the right angle are 60 and 30. Okay. Um, the side that is between the right angle and the 60-degree angle is x. The side that's between and of course x could be anything, right? X could be 1, x could be a million. Uh, and the side that's between the right angle and the 30-degree angle is x root 3. And the hypotenuse is 2x. Okay? And one place you could trip up is you might accidentally think that 2x is swapped with x root 3. So you want to remember that the hypotenuse is 2x. So for example, if x were 4, it would be, the triangle dimensions would be 4, 4 root 3, and 2 times 4, which is 8. Okay, so what do we have here? We have perimeter. Well, you know what perimeter is. Perimeter is the sum of the lengths of all sides of a shape. Okay, so you can take the perimeter of any closed polygon, right? So the perimeter of a triangle, the notation that we would use there would just be side AB plus side BC plus side CA is going to equal perimeter. And we have a special word, as you can see from this variable, or from this little notation here, this C, we have a special word for the perimeter of a circle. It is the circumference, which is calculated by 2 pi r, right? So basically, if you have a polygon, you're just adding up the length of all the sides. If you have a circle, it's 2 pi r. Here's an example with a polygon, right? So we have a polygon. We know that this is an equal, a polygon with equal sides because we have this symbol here on every single side showing that they're the same length. One of these sides is 3 centimeters. Simple, we just count up the sides. So we have 1, 2, 3, 4, 5, 6, 7, 8 sides. 8 times 3 centimeters equals 24 centimeters. That would be the perimeter. Area. I want to go over a couple area formulas here. We're going to start with this one right here, the area of a rectangle. You know that one. I think you know that one, right? Base times height. You're multiplying the width of the rectangle by the length of the rectangle, the base of the rectangle by the height of the rectangle. You're multiplying the two sides together, base times height. If we know that, we actually know a lot of other stuff, right? If we know that formula, we can figure out a bunch of other stuff. One thing we can figure out is, well, is there something special about a square? We know that a square is you're just multiplying base squared, right? It's called a square. That's why we call squaring it, right? So we have the base. It's still just base times height. It's just that the height happens to be the same as the base, right? B equals h, right? So b squared is what we get for a square. Okay, so what about a triangle? You may have been using this formula without totally understanding it. 1/2 base times height. It's actually not that complicated if you're thinking about it in terms of base times height. It's just as if you're taking, imagine that you had a rectangle made up of two triangles. Well, you would find the area of the whole rectangle, which would be base times height, and then you would just split that in half to get the area of one of those triangles, right? So 1/2 of the base times the height. And it just works out in this nifty little way where if you're extending it out right here, see how this goes out further? Because you might be saying to yourself, wait, that's actually only going to give us the area of this green area right here, right here. Well, let's think about this for a second. The base extends out to right here. So what would we need to do to make this into a rectangle where we're actually taking half of the area? Well, we would just imagine it's as if we have two triangles extending to make a rectangle. We're finding the area of the whole thing, and then we're splitting it in half. And that's how it works for every triangle. You can imagine a triangle right here, okay? If we want 1/2 of the base times the height of this triangle, well, we could imagine that this triangle is actually half of a rectangle. Okay. A trapezoid is going to be similar, although actually we'll come to that last. The parallelogram is really similar to the rectangle. A parallelogram is just like a rectangle that somebody's leaning on it, right? They're tilting it over. All that we've taken is we've taken this triangle off of right here. It's still the same area. It's the same as if we took a rectangle like this. If we tilt that rectangle over like this, we haven't actually taken any area away. We've just leaned the whole thing over. So it's still just base times height. And finally, a trapezoid. A trapezoid seems a little more complicated because you all of a sudden you have three different variables and you have some division here. So you have b1 plus b2 over 2 times h. Okay, well, let's break that down. b1 is the top, b2 is the bottom. We're adding those together and we're dividing by 2. Well, when you have two terms that are added together and divided by 2, what I think about there is anytime you have a certain number of terms, then you're dividing by that number, you're just taking the average. So we're finding the average of the length of the base, so b1 plus b2 over 2, and then we're multiplying it by the height. It's pretty straightforward. It can be figured out just from understanding how we calculate the area of a rectangle. All of this has to do with base times height. And finally, the area of a circle. Circle is a little different, totally different. In fact, it's pi r squared. I don't have much more to say about that. It's just pi r squared, where r is the radius. Okay, so let's try to calculate the area of this polygon here. So first thing that we're going to do is we're going to ask ourselves, what kind of a shape is this? Okay, so I look at this and I think, well, I know it's a trapezoid because it's 4 sides. It has 2 parallel sides and 2 sides that are not parallel. So we are going to need to, let's see here, trapezoid. Trapezoid is the one that involved the average. So we're going to want to average the 2 bases, all right? So I don't have to necessarily remember b1 plus b2 over 2 times h. I could remember that, and I do remember that, but if I didn't, I could just say to myself, well, I know I need to take the average of the 2 parallel sides and multiply it by the height. Well, I know how to find average. I know it's 20, and I'm showing you both kinds of notation here. 20 plus 10 over 2, because I have 2 terms, times the height, which is 15. Okay, so 20 plus 10 is 30. 30 divided by 2 is 15. 15 times 15 Well, let's see. I know I can do that in my head because if I do 10 times 15, I'm going to get 150 plus 5 times 15 is, let's see, 5 times 10 is 50, 5 times 5 is 25. So 150 plus 75 equals 225. Okay, 225 square units. I don't know what the unit is, but I know that area is always going to be measured in square units. Ooh, and I don't actually feel like, let's see here. Here we go. All right. Circles, one kind of nifty thing about circles is that similar to how we're seeing throughout plane geometry, one of these terms here, one of these formulas can actually help you derive the rest of these formulas. So we know that area is pi r squared. Diameter we can figure out if we have r because it's just 2r. Circumference we can figure out from r because it's 2 pi r. And r, of course, is r. But what's cool is we know that if we have the area, for example, well, if we have the area of a circle, let's imagine that the area of a circle is, um, let's imagine that it is 16 pi, right? So if a equals 16 pi, okay, and we could actually imagine we have it as a decimal. Maybe it's 16 times 3.14, whatever that turns out to be, some 50 something, about. Then, well, if we have a equals 16 pi, we can actually figure out any of these because we could say, well, let's just divide out pi. I know that a equals pi r squared. So if a equals pi r squared, then a equals pi times r squared, which is, well, I know the square root of 16 is 4, so pi times 4 squared would mean that 4 is r. So if r equals 4, well, now I can figure out any of these. I know the diameter is going to be 8 because diameter is just twice the radius. I know that the circumference is going to be 2 times pi times r. So 2 times r is 8. So it's just going to be 8 pi. And so on and so forth. Okay, so here's one for us to work out. If diameter is 10, what is circumference, what is radius, and what is radius, and what is the area? So that's a pretty easy one to start with. Diameter equals 10. So let's start by getting the radius. The radius is going to be, well, I guess actually these are in kind of a nice little order for us here, but let's start by getting the radius. If diameter is 10, then the radius is equal to 5. Circumference is 2 pi r, which is just the same as pi times the diameter. So that's just 10 pi. And area is pi r squared, so we know that area is 25 pi because 5 squared is 25. Solid geometry. Solid geometry, the only thing you need to remember for solid geometry on something like the ACT is that it's just planar geometry extended into one more dimension, right? So if you have the area of a rectangle, we know that that's base times height. Well, the area of a rectangular prism is just going to be base times height, like this, times one more dimension. So imagine you're extending that rectangle back for in like a stack in that other dimension. So we have volume is what we call that, equals length times width times height, which I was kind of substituting base times height, but it's the same thing here. Okay. Well, the same principle applies to a cylinder. A cylinder, there's not a fancy formula here. It's just area of a circle, which is pi r squared, times the height. So it's just the area of a circle times the height is equal to the volume, okay? Because it's like as if we had a bunch of circles, and we were just stacking them up for that amount of height. So here's an example. The height of this cylinder is 10, the radius is 3, What is the volume? Volume is area equals pi r squared, okay? So we know the area of the circle is 9 pi, and we know we're just going to extend that upwards for the height, which is 9 times 10 times pi, which makes it 90 pi. Okay, last thing. Concept of proofs. You heard that at the beginning. You're gonna, when you open up your ACT practice book or you're on a page describing the ACT, it's gonna talk about this thing, concept of proofs, which is, it sounds fancy, it sounds difficult. It sounds like you're gonna have to do proofs. You're not gonna have to do proofs. The only thing that this term means is it's basically like saying you need to understand that performing the geometry involves doing math, pretty much. It's like saying when they ask you for an answer to a question, you need to understand that if you start with some formula, you can go through a series of logical steps and you can get to some kind of an answer, or you can get to some kind of another formula. An example would be that if we have, um, let's see, for example, and kind of maybe forget about these examples right here. Take, for example, we know that the uh, circumference of a circle equals 2 pi r. If I give you the circumference of a circle, you can use what you know to figure out the area of that circle. You would divide it by 2 to get pi times r. You divide it by pi to get just r. You would square r, multiply it by pi, and that would give you the area. That's the steps that you would take, and that would be how you would get from one thing you know to another thing. That's the concept of proving something in geometry in terms of the ACT. Okay, so I'm going to wish you good luck, good fortune, and your best efforts in tackling plane geometry on the ACT. What's next? Finally, ACT trigonometry and algebra formulas will be available in the trigonometry and algebra lessons if there was something that you were wondering about that you didn't find here.